So, let us prove that being integrally closed is also a local property, that is let A be a ring, A be an integral domain, then the following are equivalent. A is integrally closed, A p is integrally closed, for every prime ideal of A, and A m is integrally closed M n for every m in the m maximal ideals of A. So, this max spec is usually written for the maximal ideals of A, which are maximal elements of this set, right. So, this is follows from what we saw some time back, that. So, let us look at let C be the integral closure of A in the fraction field of A. Okay. Then what is meant by A being integrally closed? A is equal to C, or in other words, one can say that A is integrally closed if and only if the natural inclusion map from A to C is surjective. Right, but then we have already seen that such a map is surjective if and only if the corresponding localization with respect to P is surjective, which is if and only if A m to C m is surjective. Okay. So, this is equivalent to saying A p is surjective for every P in. Now, the last proposition that we proved says that this is indeed the integral closure of A p, right, in K. This is again equivalent to saying that A m to C m is surjective. In the max spec of A. So, this proposition says that being integrally closed is a local property. Okay. Now, suppose I have a ring extension and I in A be an ideal. Okay. So, we have been talking about elements which are integral over A, Okay. Now, if all the coefficients, suppose I take an element x in B, and if it is integral over A, and if all those elements, all the coefficients of the integral equation belongs to an ideal, particular ideal I, then we say that the element is integral over the ideal I. Okay. So, if x in B satisfies an integral equation x power n plus a1 x power n minus 1 plus etc. a n equal to 0 with a I in I for all I, then we say that x is integral over I. So, in particular, suppose I take an integral equation of x over B and look at the ideal generated by all these a1 up to a n. Naturally, it will be it will be integral over that ideal. See, it may be that this ideal will turn out to be the whole of A. Sometime it will be, sometime it will not be. Okay. So, let us look at one situation, say for example, k x cube x square y y cube. Look at the ring k x cube x square y y cube. Okay. What would be the, can you give me an element in, let us say, k x y which is integral over the maximal ideal, for example. What is the maximal ideal here? The ideal generated by x cube x square y y cube. Can you see that? See, what is I am asking about a maximal ideal. Okay. What is a maximal ideal here? This will be, if I take if I take the quotient of this k modulo this, what would the, it will be the field k, right. So, therefore, this is a maximal ideal. Now, can you tell me an element here which is integral over this and which is not here? Of course, all the elements here they do. This is indeed an integral extension, right. So, x is integral over k x cube. Now, what is the integral closure of this, what is the fraction field of this? So, I call this A. What is fraction field of A? Is this equal to k x y? Is this equal to k x y? Does x belong to this fraction field? Will, so the question is whether x is in of A. Is it? Can we write it as something, some monomials divided by some monomials here? Okay, so this is let me this is, I will leave this as an exercise. This is, it requires some amount of computation. It is not difficult at all, but I would really want you to do this. Find integral closure of of A. So, well, what I can tell you is that these two are not equal. Okay, x, see here we are talking about polynomial, I mean variable x and variable y. For a variable x to be in the fraction field, it has to be some monomial on the top divided by a monomial on the denominator. That means there should be, I mean, like if I take a monomial here, it will be x power alpha 1 plus y power beta 1 divided by, it should be of the form x power alpha 1 minus 1 y power beta 1. It has to be of this form. But now what are the options? How can you get this? It has to be a polynomial combination of these three guys. So how can you get this? Just try to make a analysis. Alpha 1 has to be 3a1 plus 2a2 plus that is all. It has to be 3a1 plus 2a2. Similarly, beta 1 can be come from 3b3 and 2 whatever. See this x alpha 1 y beta 1, this will be some x cube power a1 x square y power a2 and y cube power a3, right. Any monomial has to be some product of these guys. So therefore alpha 1 has to be 3a1 plus 2a2 and beta 1 has to be a2 plus 3a3. Now this, see below also it should satisfy the same equation. So you have to get 3a1 plus 3a2 as alpha 1 and a2 plus 3a3 as beta 1, and you have to get alpha 1 minus 1 and beta 1 minus 1 also in the same manner. See whether you can do that. You should have alpha 1 to be this, beta 1 alpha 1 minus 1 should be again of this form, whether you can do it or not. Think about it. I mean it is a easy computation, but so, and then find the integral closure of A in its fraction field. Okay, so let us come back to this. So suppose I have an extension A contained in B. Okay, let A contained in B be rings and C I be an ideal in A and C be the integral closure of A in B. Okay. Now I am trying to collect now all the elements of B which are integral over I. So naturally it will be there in C, they will all be there in C because they are C is the collection of all elements which are integral over A. I is a subset of A, therefore. So now see earlier when we looked at this set of all integral elements, the integral closure of A in B, we proved that this is a subring of B, right. C is a subring of B. Now I am collecting all the elements which are integral over I. Is this an ideal in C? If this is an ideal, what is it? Can we have some way of expressing it? Okay. So let us look at, let X be in C be integral over I. So let me leave some space here, I will complete this. Let C be x in C be integral over I. Okay. What does that mean? That means there exists a1 up to a n in I such that x power n plus a1 x power n minus 1 plus etcetera a n minus 1 x plus a n equal to 0 with a I, yeah, that we have already said. Okay. What does that mean? This means x power n is equal to minus of this, but x is in C, all these elements I1, I2 up to A1, A2 up to AN, they are all in I. So, can you identify this as a part of an ideal? In C, or in other words I extended, right. So, therefore, this belongs to I extended in C, right. That means x belongs to the radical of I extended. So, what we are seeing here is that if x is integral over I, then x belongs to the radical of I extended. I mean I, yeah, I mean this is C is the integral closure. So, I am taking, I mean by definition this is the extension of I in set of all linear combinations of the form A I x I, where A I is in I and x I is in C. See, I have an ideal I in A, and if I have a ring C, then the I extended here is nothing but this, that is exactly what I have denoted. So, if x is integral over I, then x is here. So, there is a natural question whether if I take any element here, it is integral over I or not. Okay. So, let x be in the radical of I extended. So, this is x integral over I. So, what is meant by x belongs to I radical of I extended? This means x power, there exists some n such that x power n belongs to I power e, I mean sorry, I extended. What does that mean? That means there exists some b1 up to bn, let me denote by bm in C such that x power n is equal to summation bi xi and x1 up to xn xm in I such that this is I from 1 to m. Consider the ring A b1 up to bm, right. This is b1 up to bm, all of them are in C, therefore, this is called this B, this is a finitely generated A module. So, let me call this consider the A module, this is a ring certainly, M equal to, this is finitely generated A module because all BI's are part of they are all in C and they are all integral over A, therefore, this is finitely generated A module, and x power n, yeah. What can you say about x power n m? This is contained in, yeah, I m, right, because x power n m, x power n is some linear combination of elements from I and B 1 up to B m. Therefore, x power n is here, therefore, all the corresponding coefficients are here. So, therefore, that means if I consider the map, mu x power n from m to m given by mu x power n of m is equal to x power n. Then mu x power n m is contained in I m, M is a finitely generated A module, I is an ideal in A. So, now you can apply the determinant trick to say that, therefore, there exists A 1 up to A n in some okay, let me write this as A 1 up to A r in I, such that mu x n power r plus mu x n power r minus 1 A 1 A r is 0. Apply this on the element 1 in M, what you get is x power n r plus A 1 x power n r minus, that means x is integral over, is this clear? We are again and again using this determinant trick. We are getting a map with the property that its image is contained in I m. Therefore, the map satisfies an integral equation with coefficients coming from the ideal. Okay. So, let me complete this proposition here. Then the set of all elements in B which are integral over A over I is the radical of I or radical of I extended in C, and that is precisely what we proved now. So, if I have a ring extension and I is an ideal in A, I have a ring extension A contained in B, I have an ideal I in A. If you take all the elements of B which are integral over I, then this is indeed an ideal in the integral closure. It need not necessarily be an ideal in B, but what we are saying is that it is an ideal in the integral closure, and it is precisely given by the extension of I in the radical of the extension of I in the integral closure. That is what the proposition say. Now, let us prove another very important theorem in the theory of integral dependence, which is called going down theorem. That is, see, earlier we looked at this. Suppose I have a integral extension. Okay. If I start with an ideal here, then there exists an ideal here which contracts to P. Then we proved little more. If I have an ideal P1 contained in P2, and if I start with an ideal Q1 here, then I can find an ideal Q2 which contains Q1 and contracts to P2. So, if I have a chain here and if I have a starting point here, I can go up. Okay. That is what we proved last time. So, now suppose I start with an ideal, suppose I start with this ideal. Can we always find something here which contracts to P1? Okay. Let us prove that. That is called going down theorem. This requires little more stronger hypothesis. So, let A be an integrally closed domain and A contained in B be an integral extension. Let P1 contained in P2 be prime ideals of A, and Q2 be a prime ideal such that Q2 intersection A is P2. Then there exists a prime ideal Q1 contained in Q2 and such that Q1 intersection A is P1. So, let us try to prove this. To start with, let us recall one result that we proved some time back. This is regarding prime ideals. See, a prime, so I have, suppose I have a to B bearing extension. In fact, we do not really need to be a ring extension. Suppose f from A to B bearing homomorphism. We had discussed the extension and contraction with respect to any ring homomorphism, right. So, if I have a ring homomorphism and then a prime ideal P in A is contracted if and only if P extended contracted is P itself, right. This is something that we proved. If this is a contracted ideal, that means if this is an ideal such that it is I have a prime ideal here which intersects with A to give this prime ideal. This is equivalent to saying that you extend and contract P, you get P itself. Okay. This is something that we proved some time back. I have this ring homomorphism A P12, sorry, I am looking for, so A to B Q1. See, I am looking for an ideal in contained, okay, I wanted it to be Q2, I guess, contained in Q2. Right, I am looking for an ideal contained in, okay, I should write P2. I am looking for an ideal contained in Q2. What are the prime ideals here? S inverse P where, yeah, so but S here is B without Q2, which means, which should not intersect here means the prime ideal should be contained in Q2, right. So, the prime ideals of this ring are of the form P localized at Q2, where P is a prime ideal contained in Q2. So, here I am looking for an ideal here which contained in Q2. So, I am naturally looking for a prime ideal here which intersect to give me P1. Okay. So, P1, or in other words P1, so if P1 localized at P2 is indeed a contracted ideal, is amount to saying that there exists some Q1 here, Q1 which Q1 localized at Q2 intersected with A localized at P2 gives me P1 localized at P2, right, which is equivalent to saying that if I take P1 extended to this ring, okay, so I will simply take A P2 because it is okay. P1 is contracted is equivalent to saying that P1 extended contracted is equal to P1. Okay. But then this P1 extended contracted is nothing but P1 BQ2 intersected with A. So, to say that there exists a prime ideal here which contracts to P1 is equivalent to saying that this is equal to P1, right. P1 is the smaller ideal, right, yeah. So, to prove this theorem we need to prove that P1 BQ2 intersected with A is P1 itself. So, let us try to prove this. We need to show that P1 BQ2 intersected with A is P1. We only need to prove this. If I prove that, then because of this P1 will be a contracted ideal in A, which means there will exist something in BQ2 which contracts to this, and that will precisely be the prime ideal Q1. So, let us let us first start with an element in P1 B Q2 intersected with A. Okay. This means what is this? Yeah, so let us first start with an element here. How does this look like? This means x is in P1b and s is in the complement of Q2. So this implies x belongs to P1b. That means x, I will write it as some ai xi I from 1 to n for some ai okay, let me use bi xi with bi coming from b and xi in P1, right. So let me look at the ring A prime equal to A B1 up to Bn. I do this determinant trick again. Consider the multiplication map mu x from A prime to A prime. Okay. This is any element mu x acting on any element A is x times A or A times x, does not matter. Then what can you say about mu x of A prime? This is, yeah, so this will be x A prime, but that is contained in, this is equal to x A prime, but x is summation bi xi, where xi is coming from P and all these bi's are in A prime. So I can write this as, this is contained in P, P is P1, P1 A prime, right. Therefore, by the determinant trick mu x, or I will just simply write x. Therefore, there exists A1 up to An in P1 such that, by the way, this is a finitely generated A module, we are using that here. A1 up to An in P1 such that x power n plus 1 x power n minus 1 plus etc. An is 0, which says that x is integral over P1. So if I take an element in P1 extended, then it is indeed integral over P1. Okay. Now let us look at, suppose this x by s, x by s belong to P1 B Q1 intersected with A. Okay. See, P1 extended to B Q1 and contracted to A will certainly contain P1, right. P for any ideal I extended contracted will contain I. Similarly, I contracted extended will be contained in I. So here this will contain P1, we only need to prove that this is contained in P1, or in other words, if I start with an element in P1 B Q1 intersected A, I need to show that this is in P1. Okay. So, yeah, so let y, let us write y as x by s. Okay. So, y is this. So, I can write s as, see the problem is with this s, right. To say that x by s is in P, if I can get to a form where x by s is y by 1 for some, then we are through. That is what we have to show. So, the trouble is with this s. So, let us just study what is s. S is equal to x y inverse, I mean these are all domains. So, y inverse in the fraction field of A. Now, if I multiply this equation by the corresponding power of y inverse, I will get an integral equation for s, right. If I multiply by y inverse power, so let me call this equation 1, multiply 1 by y inverse power n, then what do I get? Then I have s power n plus a1 by y s power n minus 1, a2 by y square s power n minus 2, a n by y power n 0, right. So, this becomes integral equation of, so this is, see s you can see it as an element in the fraction field of A, yeah, and this is an integral equation as a you know contained in the fraction field, all these coefficients are in the fraction field. So, we are not okay, let us look at what are these coefficients. See a I by y power I, a I is in, so let us write this is, let us set this to be V I. This implies V I belong to y power I V I is A I, but A I is in P1. If y is not in P1, what happens if y is not in P1? That would imply that Vi, no, okay, maybe I will continue this in the next class. I will conclude this next time, the complete proof.